So have you ever just stopped and thought about how stubborn ketchup can be? Or, why you can literally run across wet sand, but the second you stop, you start to sink? Well, it turns out the answer to both is actually the same. Today, we're diving headfirst into the really weird and fascinating science of fluids that just don't play by the rules, the ones that act like a solid 1 minute and a liquid the next.
And to get our heads around this, we're going to go on a little journey. We'll kick things off by questioning what it even means to be a solid or a liquid. Then we'll get into the secret of viscosity, meet this weird family of fluids called non-Newtonians, and see how they can actually save lives. And finally, we'll look at how scientists basically give these fluids a unique fingerprint.
All right, first up, let's tackle that central mystery. We're all taught in school that things are pretty simple, right? You've got solids, liquids, and gases. But what if I told you that's not quite the whole story?
This is the big question, isn't it? Can something have this kind of split personality, acting all solid and tough one moment and then totally liquid the next? The answer, as you're about to see, is a definite and very, very cool yes.
And what's so wild is that all of these things, which seem totally unrelated, are all connected. You got a kid's toy made from cornstarch, super high-tech body armor, a devastating earthquake, and just a walk on the beach. They all operate on the exact same scientific secret.
So, to crack that secret, we need to get a handle on one really fundamental property of fluids. It's a word you've probably heard before, but trust me, it is the absolute key to everything we're talking about today: viscosity.
Viscosity is really just a fancy way of saying how thick a fluid is. Just think about pouring water versus pouring honey. Water, super low viscosity. It flows easily. Honey, that's got high viscosity. It really resists flowing. It all comes down to that internal friction.
Okay, so this is where our story kind of splits in two. On one side, you have the predictable fluids, the Newtonian ones, like water. Their thickness, their viscosity, it never changes. Doesn't matter how much you stir them or shake them. But on the other side, you've got the rebels, the non-Newtonian fluids. Their viscosity actually changes when you apply a force, like stirring or an impact, what scientists call stress. And this, my friends, is where all the magic happens.
So let's properly meet these strange non-Newtonian fluids. It turns out they're a whole family, each with different personalities that react to stress in completely opposite and sometimes bizarre ways.
Now, this table shows the main categories, and yes, some of those names are a total mouthful. Don't worry about memorizing them. The key thing to get is that some fluids change over time, like honey getting a little thinner as you stir it. But the two most important types, the ones we really care about today, change instantly with force. You've got your pseudoplastic fluids that get thinner and your dilatant fluids that get thicker.
Let's just boil this down to the two big players here. On one side, you have shear thinning fluids. These get runnier when you apply force. And on the other, you have shear thickening fluids, which do the complete opposite. They get harder, more solid with force.
And here it is, the perfect example of shear thinning. Ketchup is so thick and stubborn in the bottle, right? But when you shake it or smack the bottom, you're applying stress. And that stress instantly lowers its viscosity, making it pour right out. See? You've been a fluid dynamics expert this whole time and you didn't even know it.
But hey, this isn't just some cool party trick with your condiments. Understanding these properties has some incredible and sometimes life or death consequences. Let's go back and connect the dots to those examples from the beginning.
Okay, take liquefaction. Certain types of clay are pseudoplastic, or shear thinning, so they seem perfectly solid, totally fine to build a house on. But during an earthquake, that intense, sudden stress causes the clay to lose all its viscosity and basically behave like a runny liquid. What was solid ground 1 second is completely, disastrously unstable the next. But what about the opposite effect? That's where shear thickening fluids come into play. Remember, these are the ones that get thicker and harder under stress. And this property? Well, it's nothing short of revolutionary.
So the crucial point is this. Just imagine a material that's flexible enough that you can move around in it comfortably. But the instant it experiences a high-speed impact, a sudden intense stress, it instantly locks up and becomes as hard as a solid.
And that is the principle behind liquid body armor. It gives police or soldiers total flexibility, but provides instant, rigid protection when it matters most. It's the exact same science behind oobleck, where you can punch the surface and it feels solid, and it's why you can jog across wet sand. Your quick footsteps are a stress, but you sink if you stand still and just let the sand flow around your feet. It's all connected. Now, to actually create things like liquid body armor, scientists and engineers have to be super precise.
They need to identify, measure, and categorize these fluids. And to do that, they have to know a fluid's vital statistics. It's almost like giving it a fingerprint.
A really great way to think about this is like a fluid's ID card. It has just a few key stats on it that tell you its fundamental properties, beyond just its weird viscosity behavior.
First on the card is mass density. This one's pretty simple. It's just how much stuff, mass, is packed into a certain amount of space. A cubic meter of water is way denser than a cubic meter of air. Easy enough.
Next up is specific weight. Now this is a lot like density, but it adds gravity into the equation. It's not about how much stuff is there, but how much that stuff weighs in a certain volume. And since weight depends on gravity, the specific weight of your water bottle would actually be less on the moon. And finally, we have specific gravity, which might be the most useful one of all. It's just a simple ratio that compares a fluid's density to a standard, and that standard is the density of water. This gives you a clean, pure number with no units. It's just a quick way to answer the question, so how much denser is this thing than water?
And these numbers give you a real sense of scale. Check this out. The specific gravity of mercury is 13.6. That one simple number tells you that it is an incredible 13.6 times denser than the same amount of water. It's just a powerful shorthand for understanding what a fluid is really like.
So, in the end, fluids that seem to break the rules are really just following a different and way more interesting set of rules. From the ketchup on your food to the future of body armor, this science is absolutely everywhere. And that leaves us with one final thought. Now that we get the principles, what comes next? What other mind-blowing materials are just out there waiting for us to invent?